What if humanity's emergence never represented a predetermined evolutionary destination? What if it was instead merely the culmination of an extraordinarily long chain of random events, of survival pressures, and of infinitesimal transformations that went completely unnoticed among Africa's ancient landscapes? One particular lineage of apes underwent modifications that, across vast spans of time, fundamentally reshaped the entire world. Yet this transformation unfolded gradually and quite differently from how most imagine it. This change does not commence with triumph. It begins obscurely, on damp earth, amid branches that still cradle bodies built for climbing, somewhere in ancient Africa, long before humans walked the land, long before stone tools appeared by rivers, long before firelight danced across cave walls. At this point, ape populations inhabited a world growing increasingly unstable. The forest persisted, but no longer stretched unbroken. Dense thickets thinned, passages narrowed, seasons became less predictable, rainfall patterns shifted. In certain areas, forests receded just enough to expose new distances, new dangers, and new possibilities. Nothing in this moment foretold what would come. Nothing suggested that one of many lineages had begun its extended journey toward humanness. Yet here lies the puzzle's core, not in dramatic leaps or miraculous transformations, but in a landscape that gradually loosened the old constraints. It seems simple to imagine a sharp boundary, as if some morning an ape awakened as something entirely different, a newborn creature. Reality operates otherwise. Evolution never functions like a light switch in darkness. It accumulates through countless variations, through immeasurable generations, through small advantages that initially seem insignificant. What would eventually become a defining characteristic often started as barely perceptible shifts in behavior, posture, diet, or developmental timing. The creature at this beginning is not a proto-human, not some clumsy rehearsal of humanity. It is an ape superbly suited to its era, navigating among predators, fruiting seasons, rival groups, storms, droughts, while protecting its young and judging distances. Its existence remains anchored entirely in the present. The future is invisible to it. This met us because one of humanity's most persistent misconceptions holds that humans descended from contemporary apes, that chimpanzees or gorillas represent unfinished versions of something perfected elsewhere. The actual evidence presents a stranger and far less flattering picture. Humans did not descend from modern apes. Humans and modern great apes descended from common ancestors lost in deep time. Those ancient populations vanished. Their bones are scarce. Names, should science assign them at all, remain merely provisional markers in a fragmentary record. Scientists still debate the precise branching pattern, the timing of certain splits, even the appearance of crucial ancestors. The evidence is incomplete, but the general outline grows clear enough. Among African great apes, one branch began following a distinct evolutionary path. Other branches eventually produced chimpanzees, gorillas, and orangutans. One branch, slowly and unevenly, led toward creatures that would someday ask where they came from. From a distance, this branch reads easily in description. Up close, it tangles considerably. The late Miocene and early Pliocene were not mere backdrop, but turbulent epochs marked by severe environmental pressures. Tectonic upheavals altered rainfall patterns. Global cooling transformed vegetation. Forests did not vanish overnight, but across many regions fragmented into patches of open woodland, river corridors, shrubland, and clearings. Serious challenges for animals adapted to continuous forest coverage. This represented far more than minor inconvenience. Movement routes changed, food acquisition shifted, exposure increased, and safety vanished. Repeatedly, the group faced choices, perhaps unconscious in human terms. Mothers carried offspring across open gaps their ancestors never encountered. Males attended to ground conditions with new vigilance. Bodies shaped for one existence collided with demands of another. What would later become recognizable as human did not exit the trees in one decisive step, nor did it abandon the forest behind. For extraordinarily long stretches, it belonged partially to both worlds, fully to neither. It still climbed, grasped, and sheltered in branches while keeping watch for ground-level dangers. Yet increasingly, challenges awaited it at boundaries, in unstable zones where tree cover advanced and retreated. Food distribution grew irregular, and movement across Earth acquired new consequence. In such conditions, flexibility mattered more than perfect specialization. A creature capable of exploiting varied habitats, diverse foods, and multiple strategies weathered changes that narrow specialization could not endure. The profound irony lies in how later humans, those who built cities, invented writing, created machines, often view this beginning as if reason alone explains everything. The deciding factors probably operated quite differently. They were ecological. Calories, weather, predators, offspring, and energy expenditure mattered most. Whether a body could traverse sufficient distance without overheating, carry food, survey horizons, and withstand seasonal unpredictability. The reason that would later adorn cave walls and launch satellites began here, as integral to a complete animal, inseparable from hips, shoulders, spine, teeth, gut, skin, and social bonds. No separate history of brain exists apart from body, nor culture apart from climate. From the outset, everything intertwined. Consider the emotional tenor of this ancient world too, because its history easily reduces to bones and dates, losing the life contained within. These apes knew fear. They knew hunger. They grasped the weight of protecting young. Dominance hierarchies and group tensions occupied their societies, as did attachments and recognition that their social existence permitted. Dawn brought one sort of danger, darkness brought another. Rustling in dry grass meant something. Absent fruit in a familiar grove meant something. The smell of rain, the silence of birds, tracks at water sources, all connected directly to survival. Beneath the trees, no philosophical systems were invented, but ancient wariness, memory, cooperation, and capacity to read other minds already existed, tackling immediate problems in bodies that an altering world was silently selecting. Here too fades the beautiful notion of a single fortunate mutation. Mutations certainly provide sources of new possibilities, including for behavioral innovation. Their importance is unquestionable. Every lineage depends on genetic scarcity, and without mutations, natural selection would have nothing upon which to work. Yet the emergence of the human lineage cannot be reduced to one cause. Evolution is not a magic wand producing instant transformation. It is a multi-layered process generating countless variations. Most are trifling, many vanish, and benefit in a few becomes apparent only when the surrounding world shifts. Some traits persist because they help. Others persist through linkage to helpful traits. Some spread slowly, others remain local. The story that follows weaves together anatomy, behavior, climate, migration, nutrition, cooperation, and chance. Mutation forms part of the mechanism, but not the mythical shortcut commonly imagined. Thus, the opening scene of the long human story appears neither triumphant nor heroic. It is quiet and uncertain. This is a boundary world of fractured forests and open transitions. This is one branch within a larger family of apes, not yet distinct enough to speak of with confidence as a single entity, yet already subject to pressures favoring versatility and robustness. Across these populations, generation after generation, selection began to favor bodies and behavioral traits better suited to borderland existence. No observer marked this crossing. No fossil preserves the complete transformation. Time erased nearly everything. Only fragments remain, a few teeth, some bone shards, scattered evidence of ancient habitat, and one undeniable fact. One ape lineage did not stay the same. So begins this account of forests contracting, open ground expanding, and an animal caught between old advantages and new demands. Still an ape, not yet human. Within the long, unstable gap between lies one of life's most significant events. From this shaky beginning emerges not immediately recognizable humanity, but an increasingly complex question about the nature of this emerging branch. When the old forest world began fragmenting and one ape branch faced different selection pressures, the question becomes nearly impossible to phrase in ordinary language. What exactly changed? At what point did an ape ancestor become something more definitively distinct? What do scientists really mean when they say humans descended from ape-like forebears? The answer is simultaneously straightforward and intricate. Humans are great apes, not metaphorically, not approximately, but biologically. The human lineage does not stand outside the great ape family looking in. It represents one surviving branch within that tree. The distinction lies in how this particular branch gradually acquired distinctive self-awareness, then spent considerable effort attempting to elevate itself above all others. The impulse to separate ourselves runs ancient too. Humans have long desired dramatic origins, a clear moment when the ordinary animal world ends and human history begins. Yet the deeper science penetrates, the less convincing such boundaries become. No first being awoke fully human, as popular culture prefers to imagine. No sharp line divides consecutive generations. Instead, populations existed, transforming across enormous stretches of time while combining features that would confound anyone seeking a neat ladder. Some characteristics appeared early, others arrived much later. Bodies could retain ape-like shoulders while already displaying altered pelvises. Teeth transformed while the brain remained modest. Feet told one story while hands told another. This is precisely why expressions like "apes became humans" work well as titles. Scientifically, however, they merely abbreviate a process far slower and more complicated. The common ancestor of humans and modern African great apes proves particularly elusive. Often depicted as something like a chimpanzee at the base of the human branch, this is almost certainly inaccurate. Chimpanzees evolved for exactly as long as humans did. Gorillas and bonobos evolved equally. None of these species represents a living fossil. None preserved some ancient form unchanged. Available evidence suggests the last common ancestor probably looked unfamiliar and resisted simple comparison. Some features might have resembled chimpanzees, others gorillas, still others neither. Its body, behavior, and habitat remain partially obscured because the fossil record, scattered and fragmentary, is distributed wildly unevenly across time and space. The significance of this scarcity exceeds what is commonly appreciated. Fossils don't arrive as complete life stories. They're fragments, often broken, warped, missing the soft tissue that made creatures whole and alive. Sometimes just a handful of teeth survives where an entire skeleton vanishes without trace. A jaw might endure, while feet, hands, and spine disappear. Sediment preserves one landscape and erases another. The forest environments where early apes and early hominins probably thrived rarely create ideal conditions for fossilization. Scavengers drag bones away, weather and soil destroy them. They scatter and dissolve, or get buried so deeply that almost nothing survives. The evidence is incomplete, and this incompleteness isn't a minor inconvenience. It shapes everything we understand. Paleoanthropology amounts largely to reconstructing an entire way of life from remains that fit in the palm of your hand. Yet certain discoveries stand out. Sahelanthropus from Chad is among the most controversial and intriguing finds. Its skull is so ancient it dates roughly to when the human lineage and the chimpanzee lineage probably split. The short face immediately caught attention, and where the large hole at the skull's base sits, where the spinal cord enters, some researchers read as a hint toward more upright posture. But scientists still argue about what Sahelanthropus really was, how it moved, and where it belongs on our family tree. Then Kenyanthropus from Kenya and Ardipithecus, especially Ardipithecus ramidus from Ethiopia, add new fragments and new puzzles. Ardipithecus matters most because it doesn't fit the old picture of a simple chimpanzee-like ancestor. Its anatomy shows a creature built for both climbing and some form of walking on the ground, living in woodland, not only open savanna. This detail quietly overturned earlier thinking. It showed that key steps toward being human might have happened in far more diverse settings than old textbooks claimed. What's less known is that some crucial discoveries tell us what early ancestors weren't. They weren't simply apes walking on knuckles who started standing up. More puzzling still is the long-running question of whether the last common ancestor of humans and chimps moved anything like either does today. Modern chimp knuckle walking might be their own specialization, not a window into ancient behavior. If true, one of the biggest simplifications about human origins crumbles. The starting point wasn't a frozen-in-time modern ape, but a lost form, partly familiar, partly alien, almost impossible to reconstruct except through hints. Reading fossils demands both rigor and humility. A leg bone might point to one way of walking. Without a complete spine and feet, the picture stays uncertain. Tooth enamel hints at diet, but diet alone doesn't explain all behavior or how groups organized. Skull shape can suggest where muscles attached and how the body carried itself, but it doesn't open up thoughts directly. The shift from ancient ape populations to later hominins can't be explained by a single cause, because the record of the past wasn't written for human curiosity. It formed through chance, geology, burial, erosion, and what happened to survive. We end up with a chronicle missing whole chapters, torn out pages, and endless arguments about how to arrange the surviving lines. Yet through all the gaps, something solid begins to emerge. Scientists call hominins the branch closer to us than to chimps. It includes living humans and extinct relatives that came after we split from our last common ancestor with chimps. With this branch, we're no longer talking about apes in general. We're talking about one specific line beginning its own evolutionary path. At first, the differences might be so subtle they show only in bone, but subtle isn't insignificant. Small changes in posture, movement, teeth, or development timing can open entirely new evolutionary possibilities. This view carries deeper meaning too. When humans sit within the ape family rather than above it, the old story of our exceptional separation grows harder to maintain. Your face in the mirror isn't the result of fleeing nature. It's what came from long entanglement with it. Ancient inheritance survives in grasping hands, forward-facing eyes, expressive faces, prolonged childhood, dependence on society, flexible behavior, and powerful ability to understand another's mind, something that began as survival skill among social primates. Over time, the ape fades. Just one ape line grows ever stranger in how it moves, creates, remembers, and eventually imagines. So long before the word human, before Homo, before first language traces in archaeology, the foundation was laid in bodies still close enough to the rest of the ape world to remind us how recent our differences are. The fossil record can't paint the full picture of this beginning. It won't show fur color, voice quality, or the complexity of social life. It won't tell how a young one sounded in its mother's arms, or how the group traveled through evening woodland at the forest's edge. But what survives points to a branch still deeply ape-like, yet increasingly strange, already carrying hints of a future that creatures of that time couldn't have imagined. The world shaping this early branch changed in no single direction, and that's precisely why it matters. It's not a simple story of endless forest giving way to endless savanna. Contrary to old illustrations, ancient Africa was far more complicated. Climatically and geographically restless, it shifted through long cycles, opening and closing new possibilities. Rainfall moved, temperatures swung, river courses changed, forests shrank in some areas and held on in others. Open spaces grew, but unevenly, not forever, and not everywhere at once. Across vast timescales, one environment didn't simply replace another. A mosaic world emerged of forest edges, broken woodlands, brush, grasslands, lake shores, and more grassy patches requiring different survival strategies. For ape lines living through these shifts, the trial wasn't just harsher conditions, it was unpredictability itself. The difference seems fine, but matters greatly. Animals can specialize tightly for stable conditions. They can thrive brilliantly where things stay constant and thousands of generations hold to the same body rhythms and behaviors. A changing world rewards something else. It favors flexibility, broad options, resourcefulness, and the knack for seizing chances that briefly appear and vanish. A fruit source once reliably returning each season might fail in a drier year. A shaded path between feeding spots might break. A waterhole might shrink with seasons, forcing prey and hunters into tight space. This shows too in how all creatures living in one place face the same shifts. Evidence stays incomplete, and no single climate shift by itself explains human evolution. Yet the geological and paleoecological record suggests repeated upheaval rather than one clean change. This tumult could have been a hidden engine of history. Earth itself added pressure. Especially in East Africa, movement of the crust, uplift, volcanic activity, and slow rise of ridges and mountains reshaped local climate. Lakes came and went, valleys deepened, and rain shadows formed. Some places saw stronger seasons, others stayed lush refuges. So two populations positioned not far apart on the map could live in quite different conditions. One group still found relative safety under tree cover. Another had to cross open ground more often. A third might have lived at the edges where different worlds touch, and getting by often meant using whatever chance appeared. It's in such settings that selection begins favoring creatures not perfectly suited to one world, but able enough in several. Here, movement becomes key. Not heroic journeys or grand migrations of later times, but daily questions. How far is food from safety? How do you carry young ones? How do you cool your body under heat? How often do you need trees? How early can you spot danger? How well can you gather scattered resources? The old tree heritage stays valuable. Climbing still saves lives. Height still provides shelter. Branches still give food and safety. But traveling on the ground happens more often. Even steady pressure like this reshapes anatomy over long spans. The point isn't that forests vanished and drove apes down to grassland. The point is that mixed terrain rewards you over and over for thriving in both places. Eating habits shifted too, though not yet in any sharply human way. Early members of the hominin line didn't suddenly become hunters commanding the landscape. They stayed small primates, limited by what their world offered. But a more changeable world encouraged diverse food strategies. When reliable food became scarcer, backup sources mattered more. Tough plant fiber, underground tubers and roots, seeds, insects, scavenged meat, and scattered seasonal resources could matter more in lean times than fruit bounty during good years. These pressures showed up in teeth, jaws, and how food got chewed. Some later hominin species grew heavily specialized for powerful crushing, while others seemed to keep more flexible diets. Scientists still debate how different species shared food and how much local differences mattered. But the pattern looks clear. Unpredictable terrain shapes not just where bodies move, it shapes what those bodies must process. This carried social weight too. Evolution is easy to picture as written only in bones, but as uncertainty grew, behavior itself became a selection force. Group unity, watchfulness, tolerance, communication, shared care. These grew more valuable when resources stayed uncertain and risk was hard to foresee. Lines living in more open or mixed settings had to watch for threats differently, coordinate movement differently, adjust daily rhythms for openness, heat, and food access. This didn't yet need language as we know it, didn't need culture in all its later symbolic richness, but it meant that social intelligence inherited from ape ancestors worked under conditions where getting coordinated under pressure paid off more and more. One more detail, less known but important. Climate chaos could favor not just individual traits, it could push forward the capacity for further change itself, rewarding behavioral and physical flexibility over narrow specialization too early on. In stable conditions, one perfect solution might win. In shifty conditions, the best long-term answer isn't perfection, but resilience to change. Even looking back, such pressure doesn't point straight to humanity. It doesn't guarantee big brains, tools, or fire. It merely helps us understand why certain anatomical lines, capable of trying different solutions behaviorally, could persist while others vanished. Under such pressures, evolution resembled less a march than a series of trials. These landscapes had an emotional quality that shifted with the seasons. Dry months exposed bare earth, revealing dust, bleached grass, and hard ground where traces barely lingered before the hot wind erased them. Wet months transformed lowlands into worlds of mud, reeds, insects, and fleeting abundance. At dawn, the forest could seem rich, but by midday it grew dangerous. Sound traveled differently across open terrain. A carcass meant opportunity, yet also danger. Water gathered life together and shortened distances between hunter and prey. Ancient ape groups sensed environmental change not as abstract process. For them, it was real uncertainty about tomorrow's food, survival through the next season, and which path through open country to take safely. This is why older theories, explaining human origins through a single savanna narrative, though influential for decades, now seem insufficient. Evidence points to something more complex, a world where woodlands kept their importance. Open spaces mattered too, and transition zones between them may have played special roles. Upright walking, for instance, might not have emerged simply as a response to endless grasslands. It could have developed in mixed environments where climbing, carrying, visual range, and efficient movement all mattered. Diets expanded not because one food disappeared forever, but because food reliability declined and adaptability became valuable. Social behaviors grew complex, not because evolution planned future human society, but because uncertainty punished individuals while rewarding groups. This period cannot be fully explained by one cause, since climate, anatomy, and behavior interacted at different scales that don't arrange neatly. Local conditions varied, species coexisted. Some populations grew more specialized while others stayed generalists. Some evolutionary experiments failed, others left descendants. And the record available to us is skewed toward what fossilized and what researchers found. Yet within these limits, a compelling pattern remains. The human lineage arose not in stable plenty, but in landscapes that constantly shifted conditions. Perhaps this holds the deepest meaning of changing Africa. It didn't create humanity according to some predetermined plan, but repeatedly disrupted the old equilibrium. It weakened the grip of familiar habits. It turned certainty into risk. It placed the ape lineage in environments where adaptability faced constant test, where bodies could no longer rely on what worked best in unbroken forest, and where even small gains in posture, movement, feeding, and cooperation slowly accumulated. The lineage stayed small, vulnerable, and deeply tied to its primate heritage. But the surrounding world had begun to favor something new, not everywhere, not at once, and not yet recognizable as human. The land changed before the one who would walk it. That's often how evolution begins. Long before the human brain becomes large enough to take center stage in the story, the body starts its quieter rebuild, piece by piece. This is among the strangest features of human origins. Had someone designed this sequence from scratch, mind would seem the obvious starting point. A big brain would come first, then tools, then language, perhaps a new way of moving through the world. But the fossil record shows something almost backward. The first great shift was not a leap in thought, but a reorganization of balance. It shows in hips, legs, spine, skull base, and above all in the long, awkward transition of the ape's body toward more frequent upright position. At first, this change was easy to undervalue because it announced itself without drama. Early two-legged walking, still not the refined, modern stride confidently crossing open plains. It was partial, experimental, probably inconsistent. These creatures still climbed, their arms still mattered, hands still gripped. In some cases, feet retained features useful in a world where branches remained part of daily life. Yet something significant was happening. Bodies began adapting to walking upright frequently enough that natural selection locked in changes across vast timescales far more meaningful than any single moment spent on two legs. Ardipithecus, better than most, shows how rough this stage was. Its skeleton doesn't belong to something that already left the trees, and doesn't fit the old story of a chimp-like ancestor stepping into open space. Ardipithecus ramidus from Ethiopia combines features that make sense only if this lineage was already practicing upright walking while keeping strong climbing ability. Feet show some adjustment to two-leggedness. The foot retains a grasping big toe, poorly suited for modern long-distance walking. This was not a failed human, and not an incomplete version of the later genus Homo. It was a creature of mixed worlds with a mixed-plan body. And perhaps precisely in this combination lies the key insight. Evolution doesn't wait for perfect solutions before moving forward. It works with what's viable enough. Later, among australopithecines, signs of habitual upright walking become sharper. The foot narrows and changes shape. The thigh bone angles inward toward the knee, helping place the foot beneath the body's center during walking. Lower limbs begin carrying weight more stably in vertical starts. Spine and skull base complete the picture. The head now rests differently on the torso. But even here, structure still fell far short of modern form. Australopithecines kept features of the upper body that show climbing still mattered. Not simply small humans with ape heads, but hominins who'd shifted far enough toward two-leggedness to differ from ancestors, yet remained close enough to their tree past to reveal it. Famous footprints from dry season lake beds in Tanzania make this transition almost tangible. They pressed into volcanic ash around 3.7 million years ago, showing creatures walking on two legs across damp ground, shifting weight through their feet in a remarkably familiar way. Yet familiarity might trouble us. The tracks hold a particular closeness that even skeleton doesn't convey. Bones tell of structure, tracks tell of movement. They preserve not just anatomy, but hints of behavior, cadence, pace, direction. Surviving evidence shows that by then, upright walking was no longer rare chance. It had become part of ordinary life. These walkers weren't human in the later sense, but their path through ash feels strangely recognizable. Why did this happen so early? Scientists still debate the weight of different causes, and none explains everything fully. Older theories often highlighted open savanna, treating two-leggedness as an obvious answer to a treeless world. Yet data indicates more diverse habitat, so a wider range of possibilities. Walking on two legs could save energy during moves between scattered food sources, free hands for carrying food, young, or objects, and improve vision over tall grass or low brush. It could reduce the body's exposure to direct midday sun and increase cooling airflow. It could prove useful even while foraging in woodlands, helping maintain balance and move flexibly between branches and ground. Some researchers even think brief, upright posture while gathering food or displaying gave behavioral edge long before permanent two-leggedness was locked in. None of these ideas alone looks sufficient. Together, they describe a multifunctional trait emerging in shifting ecological mosaic. Importantly, upright walking needed no single grand purpose from the start. It had only to help frequently enough in various circumstances for selection to preserve and refine it. This is how many major evolutionary shifts begin. A posture, first situation-dependent, gets used more. Small skeleton remodeling improves effectiveness. A lineage gaining even modest advantage in moving or carrying leaves more young under certain conditions. Over time, the rare becomes routine, and generation after generation, the body rebuilds around the new norm. But this rebuild carries costs. Two-leggedness isn't free. It rewires the entire frame. The spine must handle new stresses, and the pelvis must do new work. Later body development grows even more complicated. The efficiency of walking and birthing young with large brains pull anatomy in opposite directions. Knees and lower backs bear loads unknown to creatures relying on front limbs. Even now, the human body bears traces not of perfect engineering, but of historical construction. Bad backs, weak knees, chronic pain. These aren't random flaws, but part of a long compromise written into the skeleton of a primate built for one life and gradually converted for another. This is why the change matters so much. Two-leggedness isn't just another item on a feature list. It entirely reshapes how the body relates to its world. Hands participate less in movement. Carrying becomes easier. Vision changes. Under certain conditions, long journeys demand less energy. Shoulders and hips learn new coordination patterns. A creature usually standing upright doesn't simply move its legs differently. It begins to occupy space differently. And all this occurs before the appearance of the trait most often linked with humanity. The brain of early australopithecines stays small compared to the later genus Homo, and in volume closer to the chimp brain than to modern human. Whatever mental changes were underway, they hadn't yet produced the sharp brain expansion that popular imagination expects. So two-leggedness can't be seen as consequence of already formed human intelligence. The body changes first, and the story of tools, energy, childhood, memory, and culture unfolds later in a world that this upright body helps create. Easy to miss because hindsight makes everything seem coordinated, tempting to view early two-leggedness as if evolution already knew the goal. But the process requires no foresight. The ape lineage stands upright not to become human. It does so more often and more successfully because in its world, such posture begins to pay off. The future comes later. Here, something simpler and deeper begins. Changes in posture that shift what hands can do, what senses perceive, what distances mean, how to carry food and young, how to cross terrain, and, in time, how to rebuild everything else of the body. Therefore, the first undeniable step toward humanity isn't language, tools, fire, or thought we'd call fully human. It's the transition. The long art of balance that bodies spent millions of years mastering while still belonging to both trees and earth. At first it's clumsy, then it grows graceful. At first it's costly, then it transforms all. It's ancient long before anyone grasps its reach. But once this step enters habit, the lineage no longer simply adapts to a changing world. It begins shifting the conditions of its own existence within it. As the body spends more time upright, hands find themselves in new circumstances. These are still the hands of a monkey, shaped by lineages of tree dwellers and millions of years of evolution, hands crafted for grasping branches, bearing weight, pulling bodies through space, and navigating three-dimensional canopies. But as movement patterns shifted, the role of those upper limbs gradually changed. The hand no longer needed to perform the same work with every single motion. This transformation didn't happen overnight, yet it ran deep. A structure once almost entirely devoted to moving the body through trees suddenly gained new possibilities: carrying, holding, sorting, striking, pressing, and eventually shaping. It sounds straightforward, but it rests on a whole series of anatomical compromises. The shoulder matters, the arm matters, The wrist matters. The hand itself matters, down to the proportions of the fingers and how the thumb works. For a tree-climbing ape, long curved fingers were invaluable. They wrapped securely around branches, distributed loads, let the animal hang and reach and hold its own weight in ways that straighter human fingers never could. Early hominin ancestors held on to this inheritance for a long time. Their fingers didn't straighten into modern form the moment they started walking upright. The skeleton still carried traces of tree life. But gradually, as existence on the ground became more regular, as hands served climbing less and less, other demands grew important. One of the most underestimated was carrying. A vertical creature can transport objects in ways that would be nearly impossible for something moving on 4 limbs. Food could be taken from where it was found rather than eaten in place. A baby could be held safely across uneven ground. Objects could be brought to shelter, to shade, to others in the group. It seems ordinary and therefore easy to overlook, but in evolutionary terms it may have quietly reshaped how these beings lived. A lineage that could bring resources to others opened new possibilities for cooperation. A mother could move without releasing her infant. A male could carry meat or objects across distances. Group activity began centering on certain places rather than isolated moments. The evidence is incomplete and hard to read, but it's clear that carrying changed group life long before any complex technology appeared. Anatomy and behavior together show that freed hands expanded the practical world far earlier than we might think. The hand itself changed gradually. Later hominin ancestors, especially in the genus Homo, developed a stronger thumb relative to the other fingers. The wrist and palm became more stable for precise actions. The whole structure increasingly combined powerful grip with fine control. The modern human hand is unusual in joining strength with delicacy. It can swing a stone like a hammer, but also pinch, scrape, twist, thread, and guide with surprising sensitivity. This combination didn't emerge overnight. Scientists still debate when the key functional milestones were reached. Some australopithecines may have possessed finer hand control than earlier thinking allowed. Certain fossils hint at surprisingly early dexterity. The ability for precise manipulation may have been building even before the archaeological record clearly shows regular tool-making. This matters because bone often reveals capacity before behavior leaves lasting traces. The hand may have been able to do more than the earth preserved. Organic tools vanish. Simple actions disappear without a trace. A deliberately flaked stone can last millions of years, but a sharpened stick, woven fiber, or tied bundle almost never does. One of the less noticed challenges in reconstructing early behavior is that archaeology preserves what's durable, not necessarily what mattered most to daily life. Early hominins may well have deliberately worked with plant material, digging tools, or other perishable items long before stone artifacts became widespread. Manual skill didn't develop for a single reason, partly because the evidence passes through an unforgiving filter of preservation. The shoulder tells part of this story too. Human shoulders are unusual, though we barely notice since they're ours. Over time, the upper body became better adapted to a wide range of directed arm movements, repeated throws, forceful strikes, and precise reaches. Some of these abilities came later and connect more to the genus Homo than to early hominins. But the path began when hands stopped being entirely dedicated to moving the body. The shoulder, once mainly pulling weight through branches, became available for other tasks. That doesn't mean climbing disappeared, not for a very long time. For millions of years, the upper body still carried the mark of tree life, but the balance shifted. Hands served climbing less exclusively, and manipulation more. At the same time, something subtler changed in the rhythm of action and attention. A creature using its hands for many different things had to direct more nervous system resources to coordination, pressure control, sequencing, and anticipation. This wasn't abstract thinking in the later human sense, just a body entering into more complex interactions with objects. Even to occasionally hold one stone and strike another effectively required managing force. To carry food while watching for danger meant coordinating posture, vision, and grip. Scraping, probing crevices, or using one thing against another built connections between hand and brain that rewarded practice and memory. The world became less purely a space to move through and more something to work with hands. Modern apes, of course, handle objects too. They're impressive users of sticks, stones, leaves, and improvised tools. This continuity matters. Human capability didn't spring from nothing, but from a primate heritage already rich in curiosity, object play, social learning, and problem-solving. Chimpanzees crack nuts, fish for insects with sticks, and modify simple implements. Orangutans and capuchins also show remarkable manipulative intelligence. The difference isn't that other apes lacked hands and humans had tools. It's intensity, accumulation, learning, and ultimately the cultural embedding of these actions. What emerged in the hominin line wasn't the capacity to manipulate itself, but a slow reshaping of body and behavior that put manipulation at the center. Here, the hand stops being mere anatomy and becomes a meeting point between posture and possibility. Freeing the hands triggered a chain of consequences. Carrying linked movement to exchange. Grip and strength linked to experiment. Touch linked the outer world to memory. Repetitive manipulation favored structures that made it more effective. Better structure, in turn, expanded the range of useful actions. Evolution often works through such feedback loops. A modest improvement in hand control supported new behavior. New behavior rewarded better control. Over time, the loop deepened until a lineage began consistently doing what its ancestors couldn't maintain and refine as well. But caution remains necessary. This stage is easily romanticized as triumphant hand liberation. Yet such language hides the reality of compromise. Early hominin hands were burdened by old inheritance and new demands simultaneously. They were imperfect tools, awaiting the construction of civilization. These transitional structures were useful in several ways, and supreme in none. They still helped with climbing, absorbed strain, and served an animal whose life was defined by survival, not invention. That's precisely why they mattered. Evolution doesn't need perfection to create something significant. It only needs to shift emphasis, redistribute effort, and place a body in new situations often enough that other capacities become worth keeping. So the hand, once mainly helping movement through branches, began its long transformation into carrier, holder, striking tool, shaper, sensitive recorder of pressure and texture, bridge between intention and matter. Still only beginning. Large-scale stoneworking lay ahead. A great cultural explosion awaited the distant future. But already it was setting in the shoulders not entirely occupied with climbing, in thumbs gaining leverage, in wrists stable under new demands, in fingers that generation after generation learned to do more than simply hold on. As hands gained greater power to shape the world, a slower and far costlier change was gathering force elsewhere. It occurred inside the skull, yet never touched only the skull. Growing human brains are often treated as the central drama of our origins, the master key to everything else. But here again, change was less sudden and heroic than popular memory prefers. The brain didn't ignite with instant brilliance. It grew in stages, unevenly, across different species and vast stretches of time. Each increase carried a price distributed throughout the body and life cycle. A large brain demands energy, demands time, demands social investment, demands longer helplessness after birth and extended learning before maturity. In this sense, mind arrived not as gift. It came as a burden that a lineage had to learn to carry. This burden emerged before any dramatic brain enlargement. Even early hominins with brains near chimpanzee size weren't mentally static. Size alone isn't what mattered, but organization, developmental timing, and the growing role of learned behavior within social settings. The primate line already possessed powerful cognitive foundations: memory for places, understanding of hierarchy, reading faces and gestures, sensitivity to alliances, flexible feeding strategies, the ability to learn by watching others. These were hardly trivial. Later human thought built on this framework. Over time, mind didn't arise from nothing, but balance shifted. Learning and memory grew more important. Group life carried more weight. Childhood lengthened. Young remained dependent longer, and this extended dependence became one of the strangest and most defining features of the human lineage. For most mammals, infancy is a race against vulnerability. A youngster must grow fast enough, survive, and learn to function in its environment. Primates already break this rule. They produce fewer offspring but invest more, giving time to master the social and ecological map of their world. The human line pushed further still. Long childhood had obvious costs. Years of feeding, protecting, carrying, watching, and patience before young could fully provide for themselves. For a species living among predators, climate instability, and recurring scarcity, this seemed almost reckless. Yet evidence shows that slow maturation and extended learning increasingly became the human strategy. Young developed slowly not from evolutionary mistake, but because the lineage was growing more dependent on experience. This dependence reshaped family life, group organization, and survival rhythms. A species with years of vulnerable offspring couldn't rely only on solitary mothers. Well before recognizable human society appeared, selection likely began favoring forms of cooperation that could sustain such extended development. Shared vigilance, food sharing, tolerance of young, social teaching. These became more vital when acquiring survival skills required years rather than months. Scientists debate how far back these patterns extend into early hominins and when the most human development timelines actually emerged. But the direction is clear. A larger, more complex brain creates not just smarter adults. It creates long childhood, deep dependence, and strong pressure for social systems capable of supporting both. Memory turns into something far more than a useful trait in an unstable world. It becomes the difference between thriving and perishing. Knowing where water collects when drought sets in, which trees still fruit after a poor year, where predators tend to wait, which caves shelter from sudden storms, these aren't luxuries, but survival tools. Long-lived groups with tight social bonds gain an edge when individuals can hold on to and act on increasingly complex information. The world stops triggering only instant reactions. It begins to exist in the mind across time. Paths can be recalled, seasons predicted, places revisited, and social debts carried forward. Injuries, dangers, and opportunities linger in memory after they vanish from sight. This isn't yet narrative thought in the full human sense.
but the mind grows richer in time. Many animals remember, and primates especially well. What matters is the degree to which memory shapes a lifestyle built on flexibility, slow growth, and continuous learning. A young individual doesn't just inherit a body, they inherit a world of routines, routes, acceptable rules, and techniques learned gradually over time. This raises the value of elders. An older individual who has survived many seasons carries not just genes, but knowledge.
In lineages where experience matters, age becomes an intellectual resource. Brain growth, especially pronounced later in the human line, strengthens all of this. Compared to early australopithecines, human species generally moved toward larger brains, though growth wasn't steady or uniform across all branches. Some species expanded rapidly, others plateaued. Some paired larger brains with bodies suited for long travel and broad ecological range. The old picture of a steady climb no longer fits. No single cause fully explains why or when brain expansion happened. Diet matters, especially access to calorie-rich foods. Social complexity counts. Tool use matters. Environmental unpredictability plays a role. Changes in development timing too. Most likely, brains grew within networks of feedback loops rather than in response to one isolated factor. Beneath the romance lies a harsh fact. Energy. Brain tissue is expensive. In modern humans, the brain consumes a startling fraction of the body's energy budget, especially in childhood. A lineage cannot support a larger brain without paying for it through better nutrition, reduced costs elsewhere, shared food provision, altered development schedules, or some combination. So the story of mind cannot be separated from food, fire, hands, and social life. The brain isn't a crown placed on an already complete creature. It's fed by work, gathering, collective effort, and a group's willingness to keep helpless young alive long enough for their nervous systems to become useful. This creates a strange paradox. The smarter a lineage becomes, the more helpless its infants are. Human babies are born remarkably unfinished compared to young in most other mammals. Partly this follows from the compromises of walking upright and pelvic structure. Partly it's a growth strategy that lets the brain expand rapidly after birth. As a result, our most mentally capable adults grow from some of the most dependent infants. This dependence isn't a side effect, but central to the system. Extended childhood becomes the price of a mind that can absorb language, social subtlety, tools, norms, and complex knowledge about the world. Alongside this runs a quieter change harder to preserve in stone. With deeper learning, behavior depends less on instinct and permits more local variation. Two groups of the same species might act differently. Small differences in food gathering, tool use, routes, or social tolerance persist because young learn from those around them. This is culture in its broadest and least glamorous sense, not art or myth yet, but shared practice passed on through imitation and repetition. Evidence remains incomplete because behavior fossilizes harder than bone. Yet anatomy and archaeology point to a lineage increasingly dependent not just on inherited traits, but on learned ones. So the growing brain doesn't arrive as a crown placed on a ready-made form. It emerges from ancient primate abilities and drags the entire life cycle along with it. It lengthens childhood, deepens memory, raises the value of cooperation, makes age more useful, renders infants more fragile, makes learning necessary, and makes social life both costlier and more rewarding. When these changes gain enough force to shape human evolution afterward, the lineage survives not on anatomy alone. It's held up by accumulated knowledge, prolonged development, and a mind that grows slowly precisely because it can hold more of the world once formed. By the time bodies walk more on two legs, hands do different work, and young spend more time learning the world, the old fantasy of one lucky mutation supporting less and less. The idea attracts because it offers a clear answer to a tangled question. Somewhere in deep time, a single random genetic event transformed an ordinary ape into the first human, as if evolution waited for one fortunate accident to unlock the future. The idea's appeal is obvious. It's simple and neat. All human history gets one pivot point. But nearly everything science has learned about evolution contradicts such tidiness. Mutations are extremely important. Without them, there's no variation, and without variation, natural selection, genetic drift, and changing environments have nothing to work with. But no single mutation explains the creation of the human lineage. Instead comes a slower, broader, and in its own way more remarkable process. Long accumulation of genetic changes, mostly small, interacting over millions of years with bodies, behavior, climate, and developmental systems. At the most basic level, mutation isn't rare enough to explain dramatic evolutionary shifts. It's a constant process. DNA copies itself generation to generation, and copying is never perfectly precise. Most mutations are neutral, or nearly so. Some are harmful and vanish quickly. Few prove helpful under certain conditions. Many show no visible effect on their own. So any population of any species always carries shifting clouds of genetic variance. Evolution doesn't wait for miracles. It works with existing differences and those arising anew. In stable environments, many changes stay minor. A previously useless trait can suddenly become crucial. For human history, this matters especially since many of our features aren't controlled by a single gene. Upright walking wasn't the result of one mutation, neither was a large, differently organized brain. Changes in tooth size, jaw structure, pelvis shape, hand function, developmental timing, skin physiology, metabolism, and social behavior don't reduce to one switch. They arise from networks of genes affecting growth, tissue formations, hormonal systems, neural connections, and developmental schedules. Some genes influence multiple traits. Others act early when small timing shifts cause major later effects. Some alter not protein structure, but when, where, and how strongly genes are expressed. In many cases, regulation matters as much as the genetic code itself. This is easy to miss because popular culture still pictures genes as separate instructions with simple outcomes. One gene, one trait, one mutation, one dramatic change. Biology rarely works so neatly. One gene might influence bone growth in one context and nervous system development in another. A regulatory change can alter jaw shape not by creating new structure, but by extending or shortening a growth period that ancestors already had. Developmental systems are deeply interconnected. Shift one timing, and the entire trajectory shifts. So human evolution is often called mosaic. Different traits change at different rates in different combinations under different pressures. The body doesn't transform in one coordinated package. It's taken apart and reassembled gradually, piece by piece. Certain genes have caught attention through links to later human features. Conversations about speech and language often mention FOX2. Though early popular accounts overstated its significance, it's not simply a language gene. It participates in neural and motor systems involved in complex vocal and sequential control, and its variants appear in many animals. Other genes influence brain development, skin, metabolism, immunity, and skeleton growth. But caution is needed here too.
data are incomplete, and no single cause fully explains complex traits like language, thought, or social behavior.
Evolution rarely provides one convenient genetic culprit for major historical transformation. More likely, human evolution relied heavily on accumulated changes in regulation and development. A small shift in how long growth continues before maturity can alter body proportions. Changes in skull development affect brain case shape and facial projection. Shifts in muscle attachment or bone growth change locomotion, posture, or movement. Over time, these changes interact while natural selection keeps some combinations and eliminates others. The process isn't linear. Some mutations help only in certain environments. Others bring both benefits and costs. Some spread simply because populations are small and genetic drift pushes them forward. Others stay rare until ecology around them changes. In this sense, evolution is neither pure chance nor pure design. Mutation provides the roll of the dice, selection filters it, environment sets the context, and history determines which combinations exist at any moment. So the word random needs care. Mutations arise without foresight. They don't appear because a lineage needs them. In that sense, they're random. But once variation exists, whether it survives and spreads isn't random in the same way. A body slightly better at crossing distance between scattered resources might leave more offspring in an unstable world. Development supporting extended learning might grant advantage in a complex social lineage. Physiological change might help endure heat. Nutritional or disease matter decisively in some conditions and barely at all in others. The variant's arrival is random, but not the overall pattern by which successful variants accumulate. There's another, less recognized detail making the story even more complex. Human evolution was shaped not only by new mutations arising independently, but by old genetic variation that persisted for ages, mixed, and gained new weight in changing populations. Sometimes the building blocks of future adaptations already existed in ancestors long before they became especially useful. Selection can work on existing variants rather than only fresh mutations. So major evolutionary shifts don't always require waiting for entirely new genetic change. Sometimes a new environment simply reveals the value of traits that circulated quietly in a population for ages. Later culture adds another layer, beginning to shape biology in turn. This process becomes especially visible later, for instance in the retention of lactose digestion in some populations, or genetic adaptations to diet, disease, and altitude. But the principle probably runs much deeper. When behavior changes the environment in which bodies live, biology and culture stop moving independently. Tools fundamentally reshape how humans access nutrients, process food, and manage their energy. Fire transforms digestion itself. Shared childcare determines which infants survive to reproduce. Human evolution, viewed this way, isn't simply about genes building bodies. It's genes, bodies, behaviors, and environments constantly reshaping one another. The myth of a single mutation also compresses evolutionary time dangerously. Human change doesn't happen quickly by storytelling standards. The patience required is almost impossible to grasp. A transformation that looks sudden against modern anatomy might have taken hundreds of thousands of years to spread, intensify, and blend with other changes. Entire populations could maintain transitional forms across vast timescales. Some lineages displayed features that later vanished. Others held ancient traits long after new ones had already emerged elsewhere. Family trees overflow with branches that don't lead directly to us, each carrying its own mix of inherited and novel characteristics. Evolution has no single gateway. thresholds exist everywhere. So whether one random mutation created humans has a genuinely honest answer, both yes and no. Yes, in a narrow sense, mutations always form the raw material. Every major evolutionary shift depends on countless genetic changes appearing without foresight. But no, because no single accident explains the transformation. Humanity wasn't the result of one DNA copying error. It arose from countless variations passing through unstable climate, harsh terrain, extended childhood, shifting diet, social bonds, and bodies already being remade by walking upright and hand craftsmanship. That answer might seem less satisfying than one dramatic cause. There's no neat moment of origin, no hidden switch buried in a chromosome. Yet it opens a richer picture. The human branch emerged not because one mutation suddenly destroyed the ape, but because the ape branch accumulated enough useful changes over long enough stretches under the right pressures and became increasingly distinctive. Random chance matters, but it's only the beginning. Equally important is what history then does with it. As genetic changes accumulate and bodies capable of surviving a changing world get selected, traits become visible not just in posture and movement, but in the face itself. Here, human history becomes almost disturbingly tangible. A pelvis or thigh bone tells specialists something significant happened, but the face works almost instinctively. Jaws shrink or strengthen. Tooth size and proportion shift. Brow ridges project or flatten. Some lineages begin losing the extended snout of early apes. The skull reorganizes around chewing, breathing, balance, and eventually the growing brain. No single feature makes a face human. It's the accumulated result of many small adjustments. Some stem from diet, others from development, still others from how the growing skull is built, and the reasons behind some remain debated. What emerges isn't sudden revelation, but slow retreat of an ancient ape profile. Teeth offer the best starting point. They preserve well and directly answer survival demands. Early apes, especially males, often valued large canines socially as much as nutritionally. They served display, threat, and rivalry. In the hominin line, canines shrink compared to many early ape cousins. The tooth row and jaw gradually tell a different story over time. This might reflect dietary changes, social signaling, or both. Scientists still argue whether reduced canine differences indicate aggression, mating behavior, or group structure in the earliest hominins. But the overall pattern impresses. A lineage once armed with prominent, threatening teeth gradually loses part of that arsenal. The genus increasingly serves not to display and tear with long canines, but to process an expanding and shifting food range. Yet it's not simply a story of softening. Some hominin branches, particularly the robust australopithecines, often grouped as Paranthropus, move almost opposite in their chewing apparatus. Their jaws are massive, back teeth enormous. Faces built for the most powerful bites. Some species have a sagittal crest running along the skull where mighty chewing muscles attached. For long, these forms were considered an inevitable stage toward humans simply because such heavy facial anatomy looked so specialized and impressive. Later evidence pointed differently. Perhaps it was a side experiment. A lineage narrowly adapted to tough or scarce food rather than a direct path to later Homo. This pattern repeats constantly in human evolution. A powerful trait by itself might become specialization that narrows a species' possibilities rather than advancing it. The clearer line to Homo apparently moves differently.
Teeth shrink relative to overall jaw mass. The chewing apparatus becomes less exaggerated. The face gradually loses some forward projection. The process isn't straight, and different Homo species retain different combinations of old and new traits. For instance, Homo erectus still has an elongated low skull and prominent brow ridges. Later humans have a more rounded brain case and much less facial projection. Neanderthals go their own way. They have large faces, a protruding middle section, and robust features reflecting both heritage and adaptation. Data remains incomplete, but it shows faces don't move toward one predetermined ideal. They reorganize repeatedly under different ecological and developmental pressures. Almost certainly, diet plays the most crucial role in this reshaping. A mouth built for heavy chewing doesn't need to look like a mouth receiving food increasingly cut, fragmented, scraped, and eventually cooked. When hands gain better object control, stone tools help butcher carcasses and process plants, and food gets reduced before entering the mouth, selection pressure on jaws and teeth starts shifting. Teeth no longer bear the entire burden of processing. Sharp stone edges do work once only massive molars and thick jaws could handle. Later, fire strengthens the trend, softening and partially digesting food outside the body. This doesn't mean tools or cooking instantly reshape faces, but it explains why mouth and jaw can't be examined apart from technique and behavior. Features evolve within practical systems they themselves create. Growth patterns matter too, maybe even more than raw force. A significant portion of facial shape depends on developmental timing. Extend one growth phase, shorten another, and the entire skull geometry shifts. So the human face isn't simply a shrunk ape face, it follows a different growth trajectory. In modern humans, the face develops so it fits neatly beneath the high, rounded brain case, projects less forward, and has a relatively small jaw. This pattern connects not only to diet and function, but to the enlarged cranium, head position on the spine, and the prolonged development characteristic of our species. In other words, the face is a visible growth schedule.
Brow ridges deserve special attention, one of the most recognizable and misunderstood features of fossil humans. Heavy brow ridges in Homo erectus and later archaic people get routinely taken as marks of coarseness or weak intellect, but that's largely our projection. Eyebrows are structural elements tied to facial shape and skull form, forehead construction, and how the upper face positions under the brain case. They don't serve as simple indicators of mental capacity. Some archaic people with large brains retained pronounced brow ridges long after other features changed. They reveal more about skull architecture than character or personal worth. This reflects one constant danger when examining ancient faces. Modern people read morality into anatomy, but fossils provide no grounds for it. Another hint hides below, in the tongue, throat, and vocal tract, though certainty drops here. Bone imperfectly preserves the hard framework of speech. The hyoid bone goes one place, the skull base another. Ribcage and spinal canal size belong elsewhere. From these fragments, researchers try to judge breathing control, sound range, and physical capacity for complex vocalization. Data remain incomplete, and no single explanation pins down when fully modern speech emerged. But anatomy points more toward gradual rebuilding than sudden invention. As the face retreated, the skull held balance differently, and the vocal tract changed with the rest of the body. Conditions for finer vocal control could improve gradually. The body didn't yet speak in the full human sense, but already could prepare the channels through which language would later flow. Hidden in all this sits a small and unexpected detail: the human chin. It's so familiar it rarely seems strange, but among known hominins, a prominent chin is unusual and mainly marks our species. Scientists still debate its origin. Some see it as a byproduct of facial reduction and developmental restructuring rather than a directly selected trait. Others link it to mechanical stress or speech anatomy, yet no hypothesis fully settles the matter. The chin reminds us that not every distinctive human feature needs a dramatic adaptive history. Some arise as secondary consequences of deeper structural shifts. Evolution overflows with such byproducts, seeming meaningful precisely because they connect to major changes elsewhere. Faces carry social weight too. In primates, the face is dense with information, attention, mood, rank, intention, recognition. As hominin faces changed, so did the muscular and bone framework of expression. Recovering the emotional life of extinct species from bone alone is difficult, but how much facial signaling matters in primates makes it unlikely such changes were socially neutral. A flatter face, different brow structure, shifts around the mouth, and finer control of lips and tongue could have influenced signals between individuals before symbolic language arrived. The surviving evidence points to bodies becoming not only economically different, but newly readable to each other. So the human face wasn't a suddenly donned mask, and isn't one straight path away from ape ancestry. It's a continuous record of compromises. Teeth shrink with food and behavior changes. In some branches, jaws lighten. In others, they become hyper-specialized. Skull shape simultaneously adjusts to walking, chewing, and brain growth. Below the surface, the vocal apparatus slowly reorganizes. With visible form, expression and communication probably shift too. By the time late Homo emerged, transformation was unmistakable, though still unfinished. The old ape framework didn't vanish, but got repeatedly revised. And in these corrections, the face begins bearing the first clear marks of a creature that no longer just adapts to an inherited world, but can change it in response. When the face starts changing, the deep cause hides not only in bone, but in energy. Every body follows ruthless arithmetic. Muscles need fuel. Brains need more. Extended childhood demands constant support. Crossings through harsh terrain cost calories. Pregnancy and nursing cost calories too. A lineage can become more active, more social, more mobile, and more mentally expensive only when it finds ways to access more available energy or use it more efficiently. The story of becoming human, therefore, can't be told through posture and skull alone. It also runs through hunger. The question of survival boils down to basics: what could be eaten, how to find it, how to divide it, and how much effort the body must expend to turn food into life. For a long time, early hominins remained generalist scavengers, living at the edge of ecological limits. Plant-based foods stayed essential. Tubers, fruits, seeds, nuts, shoots, and gathered resources likely formed a substantial portion of the everyday diet, varying by species, location, and season. Insects, eggs, and small animals mattered too. No single prehistoric menu existed for all human lineages. Scientists debate the exact diet of many early hominins because the evidence is indirect. Teeth, wear patterns, stone tools, bone cuts, and environmental reconstruction tell the story, not preserved meals. The data is incomplete, yet over time, one clear pattern emerges. Certain branches of the human mind grew increasingly skilled at obtaining meat, particularly animal tissues rich in fat and protein. This shift may have transformed the body's entire energy economy.
Meat features prominently in origin stories as the magical ingredient that built the brain. The reality is more nuanced. People are not alone in eating animal tissue, nor are our cousins, the apes. Chimpanzees hunt and consume meat. Many primates take animal food whenever available. What matters is not whether human ancestors ate meat at all, but how often, how efficiently, and what consequences followed. Before systematic hunting, scavenging offered major advantages. A carcass abandoned by lions or other predators provided bone marrow, remaining flesh, organs, and fat to anyone smart enough to arrive in time and capable of cutting or breaking what teeth alone could not. Here, technique meets nutrition. A simple stone blade opened up calories locked behind skin and sinew. A hammerstone shattered long bones and exposed the marrow inside. This matters because bone marrow and fat pack high energy density. This is not mere sustenance, but concentrated fuel. For a lineage that moves more, grows a bigger brain, and supports dependent young longer, these quality calories could prove decisive. No single cause explains human brain expansion entirely, but wider access to energy-dense food almost certainly forms part of the answer. The body can survive on little, but bodies carrying expensive tissues and behaviors need more energy. Animal foods supply it, especially when combined with tools that reduce extraction costs. The archaeological record shows this shift through scattered yet significant finds. Alongside stone tools from early Homo and possibly earlier hominins lie animal bones bearing cuts and impact marks. These marks are small but eloquent. A cut on bone suggests sharp edges were used to strip meat.
Spirofractures and percussion dents indicate long bones were deliberately cracked open. Yet caution is warranted here. Cuts alone don't always prove active hunting. Tool-using scavengers leave similar marks. Often the question is not whether ancient people were pure hunters or pure scavengers, but how they blended both strategies depending on risk, skill, competition, and circumstance. A carcass on the landscape means temporary fortune, but serious danger too. Exploiting it required timing, courage, cooperation, and possibly the willingness to indirectly challenge predators without overpowering them. This likely had social consequences. Animal meat is bulky, perishable, and difficult to consume entirely at once. It simultaneously encourages exchange, theft, hierarchy, and cooperation. A large carcass feeds more than one individual, but threatens conflict within the group and attracts rivals from outside. The more hominins depended on such resources, the more important became the pressure and tolerance necessary to distribute them. Food cannot be separated from society. Bodies improved by better energy grow alongside relationships required to obtain that energy. Then, somewhere along the long arc of history, a transformation began forming around the hearth, fire, one of the most powerful forces ever partially controlled by humans. Yet the word control requires caution here too. Early hominin encounters with fire probably bore little resemblance to permanent household possession. Natural fires existed long before people. Lightning ignited dry grass. Volcanic activity set the earth ablaze. Smoldering edges of burned terrain first offered opportunities, then power. Animals fled the flames, leaving carcasses behind. The landscape cleared. Fresh vegetation appeared after the flames passed. Early meetings between hominins and fire were likely cautious and accidental, using fire's aftermath rather than summoning it at will. When regular fire use truly began remains debated. Scorched sediments, altered bones, and heated stones are difficult to interpret confidently in deep antiquity because natural fires leave similar marks.
Some sites suggest earlier use than others, but scientists still work to distinguish regular human activity from natural processes. Preserved evidence shows that routine, socially embedded fire use became clearly visible later than many older accounts claimed. This uncertainty matters. Fire is too significant to assign without solid evidence.
Yet when hominins began reliably using it, at least sometimes, the consequences were enormous. Cooking food stands as perhaps the most important outcome, though far from the only one. Raw food sustains life, but cooking transforms it physically and chemically, making nutrient extraction easier. Heat softens fibers, breaks down starches, melts fats, weakens connective tissues, and reduces chewing and digestive effort. In practice, the body gains more usable energy from the same material while spending less time and mechanical work. This affected the face and jaw, but deeper consequences touched the gut and brain. When food digests more easily and actually yields more energy, the body's internal budget shifts. Some researchers argue that fire mastery and regular cooking supported an evolutionary trade-off. Digestive costs dropped, while more energy became available for a larger brain and longer development. The exact timing and scale remain debated, but the logic holds. Fire outsources part of digestion to the external environment. Energy processes before entering the body. The hearth transforms not just nutrition, but also time. For many primates, searching for raw food consumes vast portions of the day. Fire reshapes evening life and extends useful time after sunset. It provides warmth in cold, deters certain predators, creates a gathering point, and establishes a place where food gets prepared, shared, and eaten together. A group around fire is not yet civilization, but it transcends the limits of daylight. Preserved evidence suggests repeated fire use drew bodies and attention into a social circle. Faces became visible after dark. In flickering light, gestures worked differently. Food was no longer simply found and eaten, it was brought, transformed, and divided in a common place. This may have altered cooperation in ways that leave only indirect traces. A group maintaining fire must protect and feed it. This meant carrying embers, remembering fuel sources, and setting aside food for cooking. These small logistical acts deepened planning and interdependence. A lone individual might accidentally use a burning landscape. A group sustaining flames organizes routine around a managed natural force. The shift starts practical before becoming symbolic. It determines who gathers fuel, who waits, who eats first, who remains at camp, and who travels onward. Ritual meaning comes later, but social significance begins immediately. There were costs. Hunting meat brought injury risk, disease exposure, and competition. Fire burns, spreads, dims, and demands labor when energy is already scarce. A lineage dependent on quality food grows vulnerable if it disappears. Evolution offers no one-sided gifts, but the long-term trend seemed clear. A wider diet, better access to animal calories, and eventual fire use rewired the human lineage from within. Teeth no longer needed to handle all heavy work. Under new energy conditions, the gut could change. A larger brain became more feasible. Long childhood became biologically less expensive. Social life bound more tightly to obtaining and distributing valued resources. Human history advances not only because bodies straightened and hands grasped. It moves because this lineage, slowly and unevenly, learned to extract more life from the world than ancestors could. Neither meat nor fire alone created humanity, but together with tools, cooperation, and ecological pressure, they altered the scale of life for a primate body. A creature emerged that spends less time processing the world as found and more time reshaping the world before consuming it. By the time the human line drew more energy from meat, bone marrow, and eventually cooked food, another quiet revolution unfolded in stone. It did not begin with elegance. The earliest tools were unremarkable, rough fragments awaiting civilization's notice. Crude, broken, practical objects, often simply a stone with a useful edge. Yet within their simplicity lay one of history's deepest transformations. A deliberately struck stone is more than an object. It is a solution preserved in matter. It is thought, however brief and crude, hardened into form. The hand vanishes long ago, but the edge still speaks. Also, somewhere, did not simply accept the world as found, but deliberately changed it. Details of the earliest evidence remain disputed, and this uncertainty matters. At a site called Lamekwi, stones dated to around 3.3 million years ago suggest intentional stoneworking may have preceded the genus Homo. If correct, tool-related behavior runs deeper than old accounts allowed, possibly to australopithecines or similar hominins with brains far smaller than later humans. Scientists still debate how these stones were made, how systematic the behavior was, and whether such early assemblages represent sustained tradition or limited experimental phases. Data is incomplete, but the possibility itself is significant. Manual intelligence and object transformation did not wait for fully modern minds. They began earlier, in bodies already upright, engaging the world differently and capable of repetition and choice. Then, with the Oldowan tradition, the picture sharpens. From approximately 2.6 million years ago onward, sites show repeated production of simple stone flakes and cores. Crude as these tools appear, they reveal something crucial about thought. To intentionally produce a flake, the toolmaker had to understand that one stone could predictably alter another. The maker had to select raw material, judge the angle, control force, and recognize that the separated fragment held more value than the remaining core. No abstract philosophy was needed, but practical foresight was. Tools were not found, but anticipated. The blow aimed not only at stone, but toward an outcome not yet visible. This element of foresight matters because it shifted how mind related to surroundings. A creature using a naturally sharp object seizes opportunity. A creature creating sharpness by necessity begins seeing hidden potential in matter. The world no longer contained only ready resources. It held forms that skilled hands had yet to bring forth. A subtle but powerful shift occurs. It retrains attention in new ways. The eye begins searching the landscape not only for food, shelter, danger, water, but also for stone quality, fracture lines, suitable hammers, portable nodules, places where raw materials might be found again. Memory expands. A useful rock exposure becomes as important as a fruit-bearing grove. A riverbank is no longer just a watering place, but a source of needed stone. Toolmaking adds sequence to behavior. Looking at a finished flake in a museum case, you can easily miss this, but stone processing unfolds in stages. First, you select one stone, then another for striking. You adjust the angle, control the force. You test the resulting edge, perhaps use it or refine it further. Even the simplest stone technology requires an ordered chain of actions. Later technologies will make it longer and more complex, but the basic principle starts here. A brain capable of holding the order of steps, restraining useless strikes, and repeating successful actions gains advantage. Toolmaking is not merely a sign of intelligence already present, it can itself train the cognitive habits that later grow into more complex planning.
Movement control, error correction, the ability to imagine the finished result before it appears. Stone tools could change the mind no less than a brush. Repeated striking creates feedback between intention and result. A failed strike teaches something. A cleanly cut flake reinforces something else. Unlike many actions that vanish immediately after completion, stonework leaves a lasting result you can examine, compare, perhaps repeat. A young female watching an experienced one doesn't have to understand everything at once, but the object itself remains a guide. Its form can be felt, its edge checked. Its usefulness can be seen even after creation. In this sense, stone technology externalizes knowledge. Part of the solution now exists outside the body, in a durable form accessible to others. This durability is one of the least flashy but most important properties of tools. Most animal actions disappear the moment they end. Chimpanzees use a stick and move on. They build a nest, then abandon it. But a stone flake can outlive its creator by millions of years. Even in its own era, it lasts longer than the brief act of making, remaining part of a group's working world. It can be carried, used again, lost, found again, or recognized as something worth keeping. Technology gains a kind of memory independent of the nervous system. Solutions remain in the environment and open new learning possibilities. Surviving evidence shows that through tools, the human line begins to place mind partially outside the skull. The practical application of early tools is straightforward, but the consequences are enormous. Sharp flakes strip meat from bone, cut skin and plant material, perhaps work wood and other perishable items archaeology never preserves. Hammerstones crack bones for the brain inside and shatter hard materials. The simple nucleus and flake method doesn't impress compared to later hand axes and blades, but it opens access to resources that teeth and fingernails cannot efficiently manage. This in turn changes diet, energy availability, and time. A carcass can be butchered faster, valuable tissue removed before competitors arrive. Plant material can be transformed into food. Labor becomes more efficient at certain tasks, and for lineages with limited energy, that is never trivial. There is also a lived truth archaeology only hints at. Work with tools is never perfect. There are failures. Stones fracture wrong, hands get cut, raw materials disappoint. A group must carry stone further than expected because local material is poor. A useful edge dulls. Children imitate and make mistakes. One individual is more skilled than another. Over time, such differences matter. If the best toolmakers feed themselves and others more efficiently, and their methods are noticed and copied, skill gains social value. The group now survives not just through inherited anatomy, but through knowledge unevenly distributed. Learning enters history, though at first it may be barely visible, nothing like a formal lesson. It may be only repeated watching, tolerance for close proximity, shared work at processing sites, or the chance for young to take abandoned flakes and broken nuclei. Scientists still argue how much direct instruction the earliest technologies required and when mimicry alone became insufficient. But the more reliably stone traditions repeat across different sites and generations, the harder it is to call their transmission pure accident. Reliable technological tradition implies social learning, and learning requires attention, patience. A group structured so young spend enough time near knowledgeable ones to acquire technique.
Here, survival increasingly becomes cultural, even before culture wears its familiar trappings. For these earliest versions, it's not art, religion, or myth, but shared method. The transmission of practical solutions recorded not in genes, but in behavior. A hominin born into such a group inherits not just a body for locomotion and manipulation, but a set of learned habits tied to stone, food, and action sequences. Two anatomically similar populations can live differently if their tool traditions differ. One butchers carcasses more carefully. Another carries raw materials over greater distances. A third prefers certain stone types or maintains locations where napping repeats. This isn't yet civilization, but it's no longer just instinct. The deep consequence is that evolution itself begins moving through a new channel. When learned behavior affects survival, the boundary between biology and culture blurs. More skillful hands support better tools. Better tools enable a more demanding diet. A more demanding diet supports a more demanding brain and longer childhood. Longer childhood gives more time to learn. Learning sustains complex traditions. The loop deepens. No single factor fully explains how far this process had advanced in the first toolmakers, but the direction is clear. The lineage begins surviving not just through body structure, but through what its members can make of the world around them. This is why the first stone tools matter, not for beauty, but for their cumulative character. They show a being beginning to live in chains of actions, preserved in skill, in remembered places, in material solutions that outlast the moment. A split stone on an ancient surface is easy to overlook, but in that split lies one of the clearest early signs that the human line is changing the conditions of its existence. A hand strikes stone. Stone changes shape. Shape changes what the body can eat and make. The altered world changes the mind in turn. In this exchange between stone and intention, survival stops being merely endurance before nature and becomes increasingly its small, repeated transformation. When stone tools begin to hold intention outside the body, ancient Africa no longer contains the whole story. For millions of years, the human line forms within the shifting mosaic of African woodlands, grasslands, lakeshores, and fragmented forests. These landscapes remain the true cradle of everything that follows. But one branch eventually does more than adapt within the cradle. It leaves, not in one heroic migration or grand march toward destiny, but through successive expansions, experiments, and survivals. The ancestral homeland is not abandoned all at once. It continues bearing new lineages, innovations, and populations long after some descendants appear elsewhere. But when hominins exit Africa into Eurasia and further east, evolution ceases being regional history and becomes continental. This movement is often described too simply, as if a fully formed species crosses a boundary and neatly settles empty space. The evidence paints a far messier picture. There may have been multiple exits, not one. Some populations left and vanished without lasting descendants. Others survived only in certain areas. The evidence, especially for the earliest phases, is incomplete, and scientists still debate which species first left Africa and how many times this occurred. But when Homo erectus and related early Homo populations appear beyond Africa, the scale of change is already clear. A lineage once rooted in one ecological theatre finds itself in unfamiliar climates. New predators,
different prey, unknown plants, distances far exceeding ancestral ranges. Dmanisi in modern Georgia stands as one of the most remarkable windows into this transition.
Remains of early Homo, more than 1.7 million years old, show that hominins lived surprisingly far outside Africa very early. The inhabitants of Dmanisi are especially telling because they don't look like triumphant superhumans. Their brains are relatively small compared to later Homo. In some anatomical features, they're primitive, in others, more developed. Stone tools are simple, yet these beings already inhabit the Caucasus, at the edge of a world their ancestors never populated. This detail is extraordinarily important. It shows the first successful exit from Africa didn't require the full set of later human traits. The lineage didn't need to become fully modern to master a vastly wider map. Universal adaptability, endurance, a group's capacity to recover, and tolerance for new conditions sufficed. Such tolerance was one of the great quiet achievements of Homo erectus and related populations. If early hominins learned to thrive in diverse African settings, Homo erectus greatly expanded that flexibility. Its body is noticeably adapted for long-distance travel. Legs are longer relative to arms. Overall proportions in many finds suggest a gait better suited for efficiently covering distance. The pelvis and lower limbs support a more ground-based existence. This is no longer just a being capable of walking upright. Its body is increasingly built for sustained walking. Some researchers emphasize the role of sweating, body form, and thermoregulation, helping hominins move and forage across large territories in heat. No single explanation fully covers their success, but the body of Homo erectus looks like a traveler's body. Yet travel is not movement for its own sake. It follows resources, possibilities, and pressures. Climate fluctuations continue shaping the world, sometimes opening pathways, sometimes closing them. Grasslands expand and contract. River valleys serve as corridors. Coastlines may draw movement, though ancient coastal records are often lost to sea level changes. The Levant opens a gateway between Africa and Eurasia, but passage is difficult. It's a narrow bottleneck sensitive to climate, vegetation, and competition. Populations must contend with heat, water, prey, and unfamiliar ecological relationships. To the north lie colder, more seasonal worlds. To the east stretch steppes, woodlands, mountains, and eventually tropical Asia. The old African instability doesn't vanish, it intensifies.
Here migration becomes less a journey and more the long experience of human life under foreign skies. A group entering Eurasia meets winters unlike African dry seasons, a different rhythm of daylight, unfamiliar animal communities, new pathogens and parasites, landscapes where shelter, predators, and food demand different calculations of time. Surviving by simply repeating old habits becomes impossible. Routes must change. Seasonality must be reckoned. Diet must be rebuilt. Perhaps social structure as well. Children learn different dangers. Adults remember different places. Knowledge becomes increasingly regional. Africa marks the beginning, yet human history can no longer be confined to a single ecological memory. Moving eastward, the picture becomes even more striking. Homo erectus reached Southeast Asia and islands like Java, demonstrating an ability to expand territory that would have been unthinkable for australopithecines. Whether each such expansion required intentional water crossing or relied on land bridges exposed by lower sea levels remains contested in some cases. But the core reality stands clear. Our lineage no longer remained bound to its original limits. It spread into tropical forests, temperate zones, highlands, and open landscapes. Fossil records and archaeology reveal not a flawless conqueror,
but a persistent one. Lesser known is the simple truth that success looked different everywhere. Regional populations of Homo erectus and closely related forms displayed different combinations of traits. Some were more robust, others more gracile. Some connected to the Acheulean tradition of hand axes, while others maintained simpler toolkits for extended periods. The famous hand axe itself, symmetrical and carefully worked, marked a new step in planned technology. Yet even this tool spread unevenly. Across parts of Asia, large cutting implements were rare or absent for reasons still debated today. Perhaps suitable raw materials differed. Perhaps traditions diverged. Perhaps regional environments created different needs. Data remains incomplete, but the conclusion matters. As populations spread, our lineage did not maintain cultural uniformity. Migration not only expanded territory, it multiplied differences. These became both cultural and evolutionary. When populations separated by vast distances across mountains, deserts, forests, and time, they stopped changing together. Local adaptation worked on different bodies in different conditions. Isolation increased the likelihood that one regional group would drift from another. Some traits might spread through contact, others remained local. The species categories scientists later imposed on these populations struggle to capture the messiness of what actually happened. What looks from a distance like a single expanding lineage already contained the seeds of several later branches. This is why the departure from Africa mattered so profoundly. It did not merely enlarge the map. It created conditions where family trees became denser, more regional, and more complex than they could have been in a single homeland. There is also a human dimension to this movement, nearly invisible to fossils. To leave familiar ground in evolutionary terms, an unintentional act of exploration. Following game and water, avoiding competitors, occupying favorable habitats, reproducing in new places until new territory became home. Yet if that experience could be recovered, it would seem immense. New winds, new soil smells, unfamiliar seasonal cold, unknown animal calls after dusk, different stone underfoot, rivers with different rhythms, different grasses concealing different teeth, infants born far from the landscapes that shaped their ancestors. Knowledge thins at the edge of what was already known. Migration was not simply expansion, but carried forward uncertainty. That uncertainty is what makes the departure so significant. In Africa, instability forged the lineage. Beyond Africa, that same instability multiplied its diversity. Each new region became another test of anatomy, behavior, and technique. Some populations vanished, others persisted. Still others changed so much that later people would call them separate branches. By the time this process concluded, our lineage was no longer just a local African story of upright primates with tools. It was distributed across much of the known world, still evolving, still vulnerable and incomplete, but no longer bound to a single geography. Thus, the departure of ancestral peoples was not a side episode. It was the moment history ceased belonging to one ecological theater and began unfolding in many. Those once skilled at crossing broken woodlands now traversed continents. Hands that once made crude flakes carried local traditions into unfamiliar stone landscapes. Minds that once remembered African roots now recorded river valleys, mountain passes, and seasonal rhythms beneath foreign stars. With this expansion, our lineage entered a new phase where distance itself became an evolutionary force. Once populations settled across continents, the old image of evolution as a ladder could no longer hold.
It persists in popular imagination because it is easy to draw and understand. A figure smoothly rises from a bent ape to an upright human, with each step neatly replacing the last. But the fossil record tells a far stranger story. Human evolution is not a ladder. It is a branching, intersecting, crowded history where different human and near-human forms existed simultaneously in neighboring regions or at vast distances, encountering, disappearing, and sometimes leaving traces of each other. Family trees are not marches, but thickets. This becomes clear when different branches are arranged side by side in time, rather than arranged from primitive to advanced. Australopithecines existed for long periods while early Homo was already appearing. Robust forms adapted to powerful jaws lived alongside more slender variants employing different strategies. Homo and later Homo erectus persisted remarkably long and managed to overlap with later human branches that once might have been considered their successors. Neanderthals populated Eurasia, while anatomically modern humans appeared in Africa and then beyond. Denisovans, initially known almost solely through a finger bone, teeth, and genetic traces, also occupied this broad, late world. For vast stretches of time, Earth was inhabited not by a single humanity waiting its turn, but by several human lineages at once. This changes the tone of the entire story. Being human was not a single state steadily advancing toward perfection. It meant parallel experiments in different environments, diets, climates, technologies, and social traditions. Some branches became narrowly specialized, others maintained flexibility. Some spread widely, others remained regional. Some lasted far longer than once assumed. If one could stand in deep time and take in several 100,000 years at a glance, the dominant impression would not be inevitability, but multiplicity. Even Australopithecines show its early phase. These hominins walked upright consistently enough to mark a major break from ancient ape ancestors. Yet the upper body and skull retained many ape-like features. This was not a single, uniform creature repeated across Africa, but multiple species with different proportions and presumed behavior. Some were relatively generalist, others more specialized. Then came the robust Australopithecines, often called Sahelanthropus, with heavy jaws, large molars, and powerful chewing apparatus for a harsh and possibly unpredictable food world. For a time they shared the continent with early Homo. This alone was enough to abandon the ladder. One branch did not politely disappear before the next arrived. They coexisted. The genus Homo itself does not simplify the picture, but complicates it. Early Homo encompasses forms that fit poorly into a single neat sequence. Homo habilis, Homo rudolfensis, and other fragmentary or disputed populations indicate a time when brain volume, facial structure, body size, and connection to tools still varied considerably. Scientists debate how many species should be recognized and exactly how they relate. Data is incomplete, and no single account explains the tangled emergence of Homo from early hominin diversity. Yet the record shows branching, not a straight line. Several related populations may have simultaneously explored similar adaptive zones. Then came Homo erectus, or a group of related forms, encompassing African and Eurasian populations that researchers, depending on classification, often distinguish by name. The significance of Homo erectus lies not in being the first truly human in a simple sense, but in becoming one of the most successful and long-lived hominin lineages. It spread widely, existed for an immense span of time, and had a body well adapted to terrestrial life and long-distance travel. Yet Homo erectus was not the final answer either. It was a powerful branch, not the end of branching. In some places, it probably gave rise to later regional forms. In others, it disappeared. Its long existence meant overlapping in time, directly or indirectly, with other human lineages developing different traits. By the Middle Pleistocene, the tree becomes denser. Across Africa and Eurasia appeared populations often grouped under names like Homo heidelbergensis, archaic Homo sapiens, or other regional terms. From some of these populations emerged later lineages. In Europe and Western Asia, one branch became the Neanderthals. For a long time, Neanderthals were presented as crude failures with heavy brows, secondary characters in a drama belonging to modern humans. The actual picture is far more interesting.
Neanderthals were successful people of glacial Eurasia, hunters adapted to cold, skilled toolmakers, users of fire, and participants in complex societies. Their bodies were not primitive remnants. They were specialized products of long evolution in harsh climates. A broad chest, powerful limbs, a large face, and a distinctive skull shape reflect a lineage as real and complete in its own conditions as ours. Then came the Denisovans. Perhaps the most unsettling evidence that human history was only partly visible to us. Denisova Cave in the Altai Mountains of southern Siberia had long interested archaeologists, but a discovery made there changed the study of human origins as few finds have managed. From a tiny finger bone, later joined by teeth and other fragments, ancient DNA revealed a population genetically distinct from both Neanderthals and modern humans, yet related to Neanderthals as a sister lineage. At first, almost nothing was known of their appearance. No complete skull, no whole skeleton, no clear picture of face or body. An entire group of people entered science almost without image, first through molecules rather than bones. This itself was a watershed in paleoanthropology. For generations, extinct humans were identified by anatomy, jaw shape, size of the facial region, teeth, brows, and limb proportions. Denisovans came differently. Their existence was announced by genetic distance hidden in a tiny fossil. This was among the clearest signs that visible fossil records represent only a small part of the actual story. If an entire human lineage remained unknown until DNA analysis, how many other lineages left only weak or ambiguous traces? Scientists still dispute the full scope of Denisovans and their diversity across Asia. Yet genetic data suggests this was no minor regional oddity. They may have spread widely from Siberia to eastern Southeast Asia and adapted to extreme environments, including high altitudes, through ancestral populations linked to the Tibetan Plateau. This inhabited world of later human prehistory is better imagined not as a stage where one species replaces another, but as a landscape of neighbors, relatives, and chance strangers. Some from afar might have looked recognizably similar. Others differed notably in build, face, or movement. Through contact, some could exchange technologies or behaviors. Others remained isolated for long periods. The key point: anatomical modernity did not erase diversity overnight. Even when Homo sapiens began to spread widely, it entered a world already occupied by other people. This carries both scientific and emotional weight. It requires a different kind of humility. Today's humans have become accustomed to existing as the only surviving human species, and this uniqueness seems natural merely because we're so familiar with it. However, for most of our deep evolutionary past, this was never the norm. It was actually quite rare. What appears to have been the typical state of human evolution was instead a diversity of distinct lineages.
Our current solitary status, where a single surviving branch contemplates what has been lost, represents something unusual. The old ladder model of evolution breaks down under this reality. No single linear progression can account for why massive australopithecines walked alongside early Homo species. Homo erectus persisted across continents. Neanderthals thrived throughout glacial Eurasia. Denisovans remained hidden from science until genetic analysis revealed them. And modern humans emerged not onto an empty stage, but onto a world already inhabited by others. Evolution here resembles less a single advancing column and more like weather systems moving across one planet. They intersect, diverge, linger, and dissipate. This picture raises a deeper question. When different human groups existed simultaneously, what happened when their territories met? Did they simply replace one another? Compete, imitate, avoid, or interbreed? For a long time, science favored the simple replacement model. But bones and genes together suggest something far more tangled. The branches of the human family tree didn't always remain cleanly separated. When they encountered each other, they sometimes left fragments of themselves within one another. The discovery of genetic traces from ancient human lineages preserved in living people transformed our understanding far more than almost any fossil ever could. Extinction used to seem straightforward. A lineage disappears, and that's the end. Bones might survive if lucky. Tools might endure if stone or fire protected them from time. The landscape retained nothing except altered sediment and scattered remains of prey. Then genetics revealed a different form of afterlife. Some vanished peoples didn't leave completely. Faintly but measurably, they persisted within the bodies of those who lived on. Disappearance within the human family tree didn't always mean erasure.
Sometimes it meant absorption, integration, and survival in fragments.
Many researchers hadn't anticipated this outcome. Earlier models more commonly described pure replacement. Anatomically modern humans emerged from Africa and largely displaced older Eurasian populations, including Neanderthals, possibly through competition, superior adaptability, or broader social networks, but with minimal biological mixing. The picture was neat. Branches remained separate, and species boundaries seemed more defined than the fossil record had ever suggested. But ancient DNA delivered a different message. Living humans outside Africa carry Neanderthal heritage. The amount is small, but sufficient to demonstrate something significant. Encounters between modern humans and Neanderthals weren't rare, sterile accidents. They left an enduring mark. Family trees with clean dividing lines had to be redrawn with intersecting paths. Denisovans complicated the picture further. In Denisova Cave on the Altai Plateau, a cold, dark, and outwardly unremarkable location, the genetic record began unveiling a human population that science had scarcely recognized before. Not because they left behind abundant cemeteries or distinctive skulls, but because a tiny fossil fragment contained a genome matching neither Neanderthals nor modern humans. It seemed almost supernatural. An extinct group entered scientific knowledge not through a face or skeleton, but through nucleotide sequences. That cave became one of the most significant locations in human origins research. Not because of abundant remains, but because these few fragments revealed a hidden branch of the human family. The implications of this discovery further challenged old ideas about human separation. Denisovan heritage survives in some modern populations, particularly in Oceania and among certain island Southeast Asian peoples. Weaker or more complex signals appear in some Asian groups as well, Modern humans didn't merely pass Denisovans on the road of history. They encountered them closely enough to have children together, who then produced descendants of their own. Much the same applies to Neanderthals. At least during the later stages of human evolution, this wasn't the story of one superior lineage replacing all others without contact. It was a narrative of movement, crossing, exchange, and intermingling. Boundaries didn't vanish entirely. Different lineages remained distinct long enough to accumulate recognizable anatomical and genetic differences. Neanderthals weren't simply heavy-browed Europeans. Denisovans weren't local variants of modern humans. They represented genuine branches with lengthy, independent histories. Yet, independence didn't mean absolute isolation. The data remains incomplete, and scientists still debate how many mixing events occurred, where they happened, and in which directions. Genomes suggest multiple encounters rather than just one. Some exchanges might have been brief and localized, others repeated across contact zones over extended periods. The old image of hermetically separated species no longer withstands examination. One of Denisova Cave's most extraordinary discoveries makes this intertwining almost tangible. Among the remains were traces of an individual with a Neanderthal mother and Denisovan father, a first-generation child from two different human lineages. One person, known only through a bone fragment and DNA, reveals more about the ancient world than entire shelves of outdated theories. It demonstrates that these lineages were proximate neighbors. They encountered, reproduced, and left offspring whose very existence dismantles what remained of confidence in a neatly divided prehistoric world. Deep within that cave, in the cold Altai deposits, the human family emerges not as separate chambers, but as a house with broken walls. Ancient DNA also transforms understanding of extinction itself. If Neanderthal and Denisovan heritage persists in living humans, then the disappearance of these independent populations tells only part of the story. As distinct lineages, they vanished, yet portions survived within another branch. This represents not sentimental, but biological continuation. Inherited variants passed through generations and into a future the original populations never witnessed. In this sense, modern humans aren't merely descendants of an African lineage that spread worldwide, but composite beings in a modest yet meaningful way. The last undisputed surviving human species carries genetic impurity. It is historically mixed. Some inherited fragments may have proven more consequential than others. Many introgressed variants were likely neutral or nearly neutral, simply heritage passed along. Some might have proven harmful in their new genetic context and gradually removed by selection, while others apparently provided advantages in particular environments. One striking example concerns high-altitude adaptation in Tibetan plateau populations. A genetic variant in the EPAS1 region, crucial for responding to oxygen scarcity, appears to derive from Denisovan origins. If correct, adaptation to thin air arose not exclusively from new mutations in modern humans after their arrival. Modern humans may have inherited a useful physiological solution from an older human lineage, portions of which were already adapted to extreme conditions. This profoundly expands the significance of interbreeding. Contact between human lineages wasn't merely a matter of ancestry percentages. It could transfer from one population to another ecological expertise encoded in genomes across long selection history. Lineages entering harsh new environments didn't always need to develop each adaptation from scratch if another group had already done the work. In this way, genes become the legacy of encounter. Denisovans, whose appearance remains mysterious, may still influence the physiology of modern high-altitude dwellers. An invisible ancient relative might still help living bodies breathe. Neanderthal contributions appear in other domains, particularly in immune genes, skin biology, and certain metabolic processes, though the complete picture is complicated and sometimes contested. Some inherited variants may have aided modern humans in adapting to pathogens or climates beyond Africa. Others might have carried costs in later conditions. No single explanation fully accounts for which archaic genes persisted and why. Natural selection operates unevenly. Some fragments proved beneficial, others merely tolerated, still others gradually removed over time. The modern human genome isn't a museum with neatly labeled archaic heritage. It results from filtering, mixing, and prolonged coexistence of inherited elements with later selective pressures. Here lies an irony returning to old fantasies about chance mutation. Mass imagination often demands one decisive genetic moment that made humans truly human. Ancient DNA suggests something nearly opposite. Part of what modern humans are emerged not from a single unique innovation in isolation, but from mixing with other human groups once considered completely separate. Late human becoming incorporated borrowing from lost relatives. The genome isn't a sealed record of solitary ascent, but a multi-layered archive of encounters. This resonates particularly strongly with Denisovans because their physical world remains nearly invisible. We know they existed and were related to Neanderthals. We know they intermixed with modern humans and at least once directly with Neanderthals. Their genes live in modern populations, but their faces remain largely unknown. Their full appearance is disputed. Their tools, behavior, and regional variation are understood only partially through associated archaeology and fragmentary discoveries. The evidence is incomplete. Few human groups of such significance remain so visually obscure. Remarkably, Denisovans are known not through portraiture, but through inheritance. Perhaps living cells contain more reliable knowledge about them than currently rests in scientific museums. The emotion's weight of this is hard to escape. Somewhere across glacial Asia, in mountain passages, river valleys, forests, or cold plateaus, groups of people encountered other groups who weren't quite like them. They might have noticed differences in build, face, voice, habits, or movement. But they might have also recognized more that was familiar than foreign. Whatever the social reality of these meetings, the biological outcome is sufficiently clear. The ancient world didn't keep human branches completely separated. Sometimes it allowed them to cross. This transforms the meaning of our survival. Modern humans represent the last, indisputably surviving human species, yet not because all others vanished completely. We continue forward, bearing their traces within ourselves. Neanderthals departed, but not entirely. Denisovans left, but not entirely. Their bones are rare, landscapes are altered, their names were invented recently. Yet fragments of their deep history persist in living blood. The family tree didn't simply narrow to a single branch. It first wove together before it thinned. In this weaving, the lost remain with us, not as phantoms, but as inheritance. For most of human evolutionary history, the existence of multiple human species was ordinary. What's extraordinary is our current solitude. The deep past teems with lineages that emerge, persist, adapt, spread, contract, divide, and fade. Some leave abundant stone tools and bone fragments. Others leave almost nothing except a few broken teeth or genetic signals in later populations. And as the narrative approaches the present, one question grows heavier. Why did so many branches disappear? Why did a once dense family tree culminate in one clearly surviving human species and fade heritage from the rest? As is often true in prehistory, no simple answer exists. No single cause completely explains the loss of early human lineages. Extinction rarely emerges as the verdict of a single factor. It's typically the accumulated weight of unfortunate timing, shrinking numbers, environmental turbulence, local struggle, and the unforgiving arithmetic of small populations. Climate sits at the center of this arithmetic everywhere. The Pleistocene was an unstable epoch, an era where groups of humans perpetually sought equilibrium that rarely held. Glaciers advanced and retreated. Interglacial warmth alternated with cold. Rainfall patterns shifted. Vegetation transformed. Ice spread while forests retreated. Rivers rerouted themselves. Land bridges emerged, then disappeared beneath rising seas. A population could sustain itself for thousands of years under one resource distribution, then watch it disintegrate as the next major temperature or moisture shift arrived. Hunting grounds narrowed. Familiar prey migrated or became scarce. Plant foods grew unpredictable. Refuges closed. Barriers strengthened. Some shelters persisted, but not everywhere. A lineage could master one world brilliantly, yet falter if the world changed faster than behavior, numbers, or migration patterns could adapt. This proved especially critical for human populations living at ecological edges, scattered groups across cold steppe, mountain passes, forest margins, or fragmentary woodlands. These areas looked expansive on maps, yet remained profoundly vulnerable in reality. Spread was not equivalent to safety. Groups were separated by distance, glaciers, deserts, and hostile terrain. When contact weakened, mating networks contracted, genetic diversity declined, and local innovations spread poorly. A sequence of harsh seasons could devastate one isolated population after another without help from neighbors. Evidence remains incomplete, but paleoclimate research, archaeology, and genetics reveal a consistent pattern. Many extinct human groups were not sprawling, densely settled societies capable of absorbing shocks. They were small populations positioned at the limits of ecological viability. Pressures that large groups could absorb posed far graver threats to the small. A few failed births mattered more. A handful of injuries mattered more. The loss of a skilled hunter, a craftsperson, or an elder carried greater weight. Disease was more dangerous. Random chance was more consequential. This is among the least dramatic yet most significant truths about extinction. A lineage doesn't always vanish because a superior rival decisively overwhelmed it. Sometimes numbers fall so low that ordinary bad luck becomes fatal to the entire group. Floods, severe winters, failed migration seasons, local prey collapse, epidemic, a cascade of infant deaths, and the population crosses a threshold from fragile persistence into irreversible decline. Evolution abounds in grand patterns, but it's also full of mathematics. Neanderthals are the most renowned example because their disappearance happened close enough to our rise to feel personal. For hundreds of thousands of years, they inhabited Western Eurasia, endured repeated climate swings, hunted megafauna, crafted sophisticated tools, controlled fire, cared for the injured, and adapted to harsh conditions that would have broken many other lineages. Nothing about them suggested a species standing merely at the edge of collapse.
Yet, as a distinct population, they vanished not long after modern humans spread into their territories. Generations of researchers wanted to render a simple verdict. Modern humans were smarter, faster, more social, more inventive. They simply replaced Neanderthals. The narrative was elegant. Too elegant. Scientology still debate the precise balance of causes, but evidence points to a layered process. Neanderthals likely faced recurring climate stress, habitat fragmentation, sparse population density, weak long-distance connections, and eventually competition or demographic pressure from arriving Homo sapiens. Interbreeding occurred, so replacement was incomplete. The disappearance of a separate lineage may have involved not just mortality and exclusion, but partial absorption. Denisovans remain even more elusive, making their endpoint harder and perhaps more instructive to trace. Based on their genetic legacy in several later populations, they ranged widely and occupied environments from frigid Siberian caves to high-altitude Asia and possibly regions beyond. Yet skeletal remains are sparse, and visible anatomy so ambiguous that their decline must be reconstructed like a fading fire from scattered sparks. Did different Denisovan populations vanish at different times? Were some absorbed into expanding modern human groups? Did climate fracture their world until isolated pockets dwindled to nothing? Data is insufficient, but their story fits the same broad pattern. Even a lineage with exceptional regional adaptations cannot endure indefinitely if its populations are rare, the environment unstable, and neighboring peoples with demographic advantages occupy contact zones. Competition matters, but not necessarily through overt violence. One human group can demographically surpass another without sustained direct warfare. A population with broader social networks more stably exchanges partners, knowledge, and materials across distances. A population with flexible diets, higher density, or better resilience against local scarcity recovers more efficiently after lean years. Groups with distant alliances or reliable symbolic communication better coordinate movement and cooperation across larger territories. Even modest advantages, repeated across generations, become enormous when two lineages occupy overlapping lands. One need not destroy the other. It can simply reproduce more reliably, exploit more ecological niches, and maintain connectivity between populations while the other fragments. That's how modern human expansion could have had profound consequences without invoking instant superiority in all domains. Homo sapiens may not have possessed a single magical trait that doomed any rival on contact. Rather, a combination of flexibility, scope of social networks, innovation, symbolic communication, and demographic resilience gave certain populations an accumulating advantage as they spread. Superior long-distance exchange, varied subsistence strategies, richer symbolic use and group identity, or simply larger breeding networks might have eventually proved decisive. No single explanation fully captures why our branch survived and others faded. Yet the picture suggests cumulative advantage rather than one dramatic secret. Perhaps sheer historical contingency played a major role. A lineage can weather climate crises across hundreds of thousands of years, then simultaneously encounter an unlucky convergence of pressures. Cold arrives while prey availability crashes. A neighboring human population expands. Local refuges shrink. Disease spreads. Genetic diversity is already low. Within a few generations, the branch crosses a point of no return. In the fossil record, extinction often appears sudden simply because the record is so sparse. In real time, it may have been uneven, regional, and prolonged. Some populations vanished earlier, others persisted for millennia. There may never have been a single last Neanderthal or last Denisovan in any emotionally meaningful sense. Scattered final communities probably lingered, then final families, then final children whose descendants either ended or dissolved into another population. That last possibility matters. Human extinction is frequently incomplete. Bodies disappear, distinct cultures and local identities fade away, but genes, habits, or techniques survive in others. We already know this happened biologically through introgression. The same probably occurred with behavior in ways harder to prove. Contact between human groups transmitted knowledge alongside descent. Tool traditions, hunting methods, passages through mountains, adaptations to difficult environments. Such things don't fossilize neatly within a species label. They cross boundaries, blur, and persist after the population that refined them is gone. So the ending of other humans shouldn't be read merely as a parade of failures. Many lineages were exceptionally successful, even by animal world standards. Homo erectus existed for an enormous span. Neanderthals mastered the harsh ecology of the Ice Age. Denisovans left adaptations that benefited living humans. Their end does not erase their achievements. Extinction in evolution is not a moral judgment, but the ordinary fate of most branches, including remarkable ones. The surprise isn't how many lineages disappeared. It's that one persisted, carrying inside it fragments of all the rest. This leads to the final, unsettling truth. The forces that ended earlier human lineages were not foreign to us. Climate fluctuation, small numbers, ecological stress, fragmentation, reliance on cooperation. The perils of randomness shaped our branch too. We survived where others didn't, but not because we stood outside universal rules. We persisted as another human lineage moving through a dangerous world, vulnerable to the same pressures, altered by the same instability, never assured of a future. Our difference lies solely in the fact that our contingent continuity held. Ultimately, the deepest lesson isn't that one primate lineage grew clever enough to dominate the planet. It's that becoming human was never a clean break from the rest of life, never a single mutation, straight ascent, or the work of one isolated trait. After all the vanished branches, scattered bones, fractured stones, and ancient DNA lies a deeper pattern. Human lineage arose through weaving, bodies and landscape, mutation and time, hunger and invention, childhood and memory, isolation and intermingling, loss and survival. If the story of apes becoming human holds one final lesson, it is this. Humanity emerged not as an escape from nature, but through prolonged openness to it, through conditions so unstable that one primate lineage progressively adapted not just itself, but the very circumstances of its own existence. We often mistake this capacity for inevitability. Looking back from our world of city lights and orbiting machines, it's easy to believe the outcome was predetermined. But early history offers no such comfort. For 1,000,000 years, the human lineage remained fragile, one branch among many. Every bone bore ancient primate heritage. It awkwardly mastered upright walking, hands gradually freed from locomotion. Childhood lengthened. Memory deepened. Tools were still so crude they fit on a palm. The diet broadened. Fire was as easily lost as won. The lineage spread, divided, encountered other humans. It vanished in some places,
persisted in others. Its success was real, but never assured. The path to modern humanity was not fulfilled destiny, but continuing chance. What makes it unusual is the ability to accumulate consequences. When posture changes, hands work differently. When hands' role shifts, tools change. When tools open new food sources, the energy budget expands. With expanded resources, larger brains and prolonged childhood became viable. With extended childhood, learning deepened. With deeper learning, culture stabilized, and separating it from biology grew harder. Spreading across continents multiplied diversity. When different peoples met, genes and ideas passed between them. Symbolic thought and social memory widened enough to reach far. The species began constructing environments that would shape its own future. No single change explains everything alone. Together they forged such a powerful chain of consequence that a lineage from the edge of fragmented forests eventually transformed into a species carrying whole worlds inside its mind. Yet amid all this change, ancient heritage never vanished. Modern humans remain primates in every essential sense. The hand that types, carves, points, and writes remains the modified hand of a tree dweller. Eyes meeting a screen or scanning across the horizon still carry that same forward-looking gaze of a primate, shaped by depth and attention. A face that speaks with language, that hides thoughts, remains built upon an ancient social mechanism for quickly reading others. The need to belong, the sensitivity to rank, the deep fear of being left out, the attachment to children, the habit of watching what other bodies intend. These are not recent decorations added on top of an animal core. They are the core itself, made intricate by time. Even the most abstract human mind remains tethered to memory, to alliances, to imitation, to fear and curiosity inherited from our primate ancestors. So the idea that a random mutation suddenly made us human is both misleading and revealing. Misleading because it squeezes too much into a single imagined moment. No single change in DNA creates a human being. No single accident explains language, fire, cooperation, and symbolic thought. Yet the idea is revealing because chance truly does weave through all of history. Mutations happen without warning. Climate shifts without caring. Geography isolates populations. No mind plans this. Lines meet because their paths cross at exactly the right moment. Extinction erases one branch and spares another for reasons that start out statistical and only later become dramatic. The beginning of humans was not a design, it was a history. And history is always filled with chance. Time transforms those chances into origins through the long, grinding work of survival. The Denisovans show this more clearly than anyone. They stand out as some of the most haunting figures in human history, precisely because they prove that an evolutionary line of tremendous importance might leave almost no trace at all. A handful of small bones, a few teeth, faint marks in cave deposits, and genetic traces in later peoples. That is enough to reveal an entire branch of humanity that science never knew existed. Their bodies are mostly hidden. What we know of them is fragmented. Their culture and appearance remain open to debate. And yet they matter decisively in the story. They show that major human lineages can vanish almost completely from the fossil record. They show that human evolution includes both splitting and blending, that survival can follow paths other than simple forward progress. In this way, the Denisovans teach caution. The visible record is not the complete record.
The past is larger than the bones we happen to dig up. Neanderthals offer another lesson. For too long we thought of them as a broken version of ourselves, the wrong answer beside the right one. Now they appear not as opposites, but as relatives. People adapted to the cold lands of Europe and Asia, remarkably resourceful, tough, and flexible, though ultimately unable to survive as a separate population. Homo erectus teaches the same lesson even more deeply, reminding us that evolutionary success cannot be measured only by how similar something is to us. Few hominin lineages persisted as long or spread as far. Even the robust australopithecines, often dismissed as dead ends, speak to the creativity of evolution. Human evolution was not a show staged for modern audiences. It was a vast terrain of real lives, most of them ending without descendants, yet each one complete in its own moment. Perhaps that is the true inheritance. When modern people ask how apes became human, they often want to know when intelligence emerged, when speech appeared, when the first truly human arrived. The deeper answer is that no single moment can hold all that weight. Humanity is not a switch turned on, but a growing collection of skills, standing upright, using hands to make things, sharing food, remembering, teaching, adapting, breeding with other kinds, and imagining things that do not exist. Different parts of this set appeared at different times and in different lines. Some appeared in Homo erectus, some in people beyond our own kind. Some were more widespread in the human family than we once believed. The result is not one gate passed once and for all, but a long hallway of gates, most of them visible only when you count across many different pieces of evidence. Today, there is one human species, but there is not one human story. In every language, every settlement, every journey, in every face and body passed down through generations, in every child who needs years of care to grow into an adult, there still dwells the deep framework of that ancient history. Humans remain a species built on gradual learning, on needing others, on taking energy from the world, changing that world, and constantly rebuilding it with wisdom shared between generations. Both a gift and a danger lie in that capacity. The very same abilities that let us survive in chaotic prehistoric worlds now let us reshape the atmosphere, seas, and forests, and alter the futures of countless other creatures. An old evolutionary trade-off has grown to the size of the whole planet. So what humans became is not merely that one line made it through, but what that line learned to hold, more of the world within itself and more of yesterday within itself. Through tools, through fire, through memory, through children, through stories, through genes, through returning to places and changing them, the human line grew into something that gathers and stores. It obtained history in a way that no earlier ape ever could. After that point, when a line died out, it was not just bodies that vanished, but songs that would never be sung again, trails that would never be walked, faces that could never be found, and entire ways of being human that ended before anyone learned to write them down. The single remaining branch carries all of that loss, even without knowing any names. History circles back to where it began, in unknowing. But now that not knowing feels both wider and deeper. Somewhere in old Africa, a line of our ancestors lived at the shrinking edge of the forest and did not guess they were the start of anything. Much further ahead, in caves and across grasslands, in icy valleys, through mountain passes, and beside dying fires,
Other human lines lived out their complete and entire worlds, not realizing they would leave barely a memory behind them. From them, only scraps remain. A mark in ash, bone fragments in stone, pieces of worked flint, a single tooth left in a cave, a tiny piece of code threaded through the blood of people who never knew these names. And perhaps this is the gentlest truth in the whole long story. Humanity is not the opposite of disappearance, but a momentary refusal of it. Creatures change form, lineages branch and fade, the climate turns indifferent, kinds vanish, and what we remember is always incomplete. Yet for a moment, despite all this forgetting, one line learns to carry pieces forward. It carries them in its bones, in what it does again and again, in what it makes with its hands, in young ones who learn how to live, in old genes moving into fresh peoples, in tales created to keep yesterday close a bit longer than a single body can hold it. The forests where the first steps were taken are gone now in the shapes they had. The valleys carved by ice where different peoples once wandered are transformed past all knowing. The fires burned down. The caves still stand, a few spots where stone dust remembers and waits. And everywhere in the breathing world, these lost things echo still. Each human face carries behind it the story of much older faces. Every hand holds within it the memory of branches and stone, and the marrow inside bones, and the red of flame. Each long time a child must stay near to learn carries with it the ancient cost of becoming a being that lives by what it does not forget. So the very last picture is not a victory, but simply the continuation, briefly held back against time. A cave's cold mouth opens into gathering dark, wind across a meadow where feet once crossed, leaving nothing solid behind. A little fire somewhere in the black. Then morning, then ground, then quiet. And then far beyond that quiet, much, much later, the odd stubbornness of the ones who come after, still looking for how they got here at all.